There we go. Okay, cool. All right, so finding the perfects, you just take a number and go to the exponent, right? So 3 cubed is 27, okay? When we write it as a radical, okay, so radical is like our square root, but we don't want to call it square root anymore because now it could be fourth root, fifth root, so forth, okay? So we just call it a radical. The number that's here will determine what kind of radical it is, right? So if it's a 3, it's going to be a cube root. This number is called the index, and I'm going to use that word a lot today. So you need to know that when I say index, it means it's that number that's representing my radical, okay? Is it a cube root? Then that n would be a 3. Is it a fourth root? Then it'd be a 4. If there's no index, like if it's blank, we assume that it's a square root. Okay? And so because that's the one that's used the most, we just leave it blank. Okay? And so if there's no index, we assume that it's a square root. Okay? So these are the pieces of the radical. Okay? So first we want to practice how do we just take a square root or a cube root or a fourth root, okay? So some of the easy perfect ones are down here, okay? So the square roots are the easiest because those are the ones we're used to. So what is the square root of 16? 4. How did you know that? Yeah, because 4 squared, or 4 times 4 is 16. And because it's a squared, it happened twice, right? Okay, what about the square root of 121? 11. Good, because it happened twice. Now, I do want to refresh your memory that when we're doing it, like graphing it, it would be plus or minus 11, right? And plus or minus 4. There we go. That's a plus. Okay. So if we were graphing it, it would be that. So you guys are pretty quick with square roots because we've done this. What about cubed roots? Okay, what number times itself 3 times now, right? So to get 8, that's like saying 2 times 2 times 2. So to take the cubed root of that is just 2. When it's odd, there's no plus or minus, okay? So when the index is odd, the 3, then there's going to only be that answer, no plus or minus. Now it can be negative though. So I can have an odd index with a negative number, and that's okay. It's still real. It's still going to be a real number. Okay? So what number times itself 3 times to give me a negative 125? Negative 5. Negative 5 times negative 5 is a positive 25, but then times another negative 5 does give you that negative 125. So in this case, it'd be a negative 5. Okay? We can do it as fractions also, and I believe it was in geometry because I'm actually teaching it this week, which is kind of funny. You can split these. So this is the cube root of negative 127. You can say, okay, the cube root of negative 1 over the cube root of 27. And you can treat them as like 2 separate problems. What is the cube root of negative 1? It's just negative 1. Because negative 1 times negative 1 times negative 1. Okay? So this one would be a negative 1. And then what's the cube root of 27? 3. 3 times 3 is 9. 9 times 3 is 27. So this answer would be a negative 1/3. So the rule is if the index is even and it's positive underneath, you'll get a real root. You will get a plus or minus, okay? if the index is odd, you will get a real number, but you're only going to get one answer. If it was positive underneath, you'll get one positive root. If it was negative underneath, you would get one negative root. Okay, and we kind of saw that here. And then the starred one is because if we have an even index and a negative underneath, that's where we get our imaginary numbers, okay? Which was a whole chapter in itself. So again, your calculator, you're going to want to make sure under the math button, you know where this n root button is. And this n, you're just going to change it to whatever the index is to help you. Okay? So that works when things are perfect, right? But think about square roots. Were they always perfect? Or did we simplify them? Okay? And so that's where we're going to kind of expand on that knowledge. Okay? We're going to use the same idea, but then we're going to now simplify radicals that have a higher index. Okay? Let me see if I can move up where the graph is still on here too. All right, so 1 and 2, right, are not algebra 2 level. Those ones you should know how to do, okay? So I'm going to actually go with 3 and 4 with us right now because the index is 3. Okay, so see how the index is different? And I'm going to need room, so I'm going to actually cross these out so I can take up both boxes. Okay. All right, so the number in front will be multiplied at the end. So don't forget it, but we're going to ignore this number for a minute, this 2 in the front. Okay? And I am going to take the cubed root of 48. And so before you even start to simplify, you want to ask yourself, what are the perfect cubes? Right? So my perfect cubes are 1, 8, 27, 64, 125, I think I'm high enough right now. You can keep going. Where did I get these from? 2 times 2 times 2, 3 times 3 times 3. Yeah. I ran out. I'll have to go. It is a Google Classroom though too. Yeah. And if you need scratch paper, there's some in the green bucket back there if you want to just take some notes. Okay, so now my question is, here's the perfect cubes. And this is always good to have this list, guys, like when you're taking a quiz or a test. Right? These are my perfect cubes. Because when I'm simplifying, I'm going to still do the factor tree. Okay? So just like I did earlier, I'm going to do a factor tree. I want one of these to be one of the perfect cubes, and then one of them it doesn't matter, right? So what number times what number gives me 48? Where one of them is in this list, right? So 8, yeah. So 8 times what? 8 times 6, okay? Is one of these in my perfect? Yes. So what is the cubed root of 8? 2. Okay. Can I simplify the cubed root of 6? No, because my one, I mean 1's a weird one, but my lowest is 8. So 6 isn't going to work. So 6 is going to stay under the radical. Okay? So I would be done, except what did I say to save at the beginning? The number that was in front. Okay? And so I don't know if you remember, but in geometry, you multiply the numbers on the outside with the numbers on the outside, and you can multiply the numbers on the inside with the inside. But you can't do an outside with an inside. Okay? So I can multiply this 2 by this 2. So 2 times 2 is 4. So my final answer is going to be 4 cubed root of 6. Okay. What do you think? Very similar to square root, right? You just have to know the list of perfect cubes. So there was a 2 in the original problem at the top that we saved for later. So this 2 came from simplifying, but this 2 was already there. So then I multiplied it. So these get multiplied. All right, let's do number 4. So same idea. We have a 3 on the outside. Everyone sees the 3 that's in the problem? We're going to save that for later. You're going to multiply it at the end, okay? So I'm going to ignore it for now. And I'm going to do cubed root of 108. Now, I want to factor these so that one of them is a perfect cube. Okay, so how do I do that? I start to take 108 and I just start dividing some of these perfect ones that are in my list. That's the easiest way to do it, okay? So do any of those go into 108? 27, good. 27 times what? Times 4. Okay. All right, what is the cubed root of 27? Can I do a cubed root of 4? No, I can do a square root, but I don't have. I can't do anything. So that stays there. So remember at the beginning, what did I have? I had another 3. So I'm going to take these 2. I'm going to multiply those together. So my final answer is going to be 3 times 3, which is 9. And then I still have this cubed root of 4. So that's my final answer. I think we finished page 1. Alright, let's do a 4th root just because we've only done cube roots so far. So if we go to page 2, we're going to do either 7 or 8. It doesn't matter. Let's do 8. 8 looks big, right? 8. Okay. So number 8, we have this 5, right, on the outside, so don't forget to use that later. I'm going to need room, so I'm just going to cross it out. Okay, so we're gonna save the 5 for later. We are going to do a 4th root of 2,592. This is why we're not doing 5th and 6th roots today, because they get high quick, okay? We still want to factor this. But now, instead of using my cubic list, I want to use my 4th root list, okay? So 1 to the 4th is 1, 2 to the 4th is 16. So we have this list going on. Can we divide any of those numbers into 2,592? Yeah. So this one, okay, is going to be my perfect one. And then it was times 2. Okay? So 1,296 times 2 is this 2,592. Okay? What is the 4th root 1,296. 6. Okay. Was there a number in front to start with? Yes. What number was in front? So you times this by 5. And then we'll still have this guy also. So 5 times 6 is 30. And then we still have a 4th root of 2. And so that's your final answer. All right, go ahead and try number 7 on your own. So that you know what it is. Okay, and so this part, the index is going to be really important. So that's why I wanted to write it again. So remember, the index is whatever number is with the root, okay? And so this index number is going to be very important in this next part, okay? So everything's great, but now we have variables. So now it's going to get a little tougher, okay? We have to first look at the index, okay? So for number 9, when there is no index, we assume it to be 2, okay? So for number 9, the index is 2, okay? When the index is 2, we can call it the square root. That means all the exponents within the problem have to be a multiple of the index. Okay, so let me write that again. Exponents in the problem have to be multiples of the index. Okay? If they're not, we have to make them be. Okay? So you'll notice number 9, are both of those exponents inside? Are they multiples of 2? Or can I divide 2 into both of those? I can do it into the x. Can I do it into the y? No. So for the y, it's y to the 9th. I need to go down as much as you need, usually just 1, right? Or 2. So y, do you do that y to the 8th is a multiple of 2? Okay? So I'm going to factor out, so kind of like the greatest common factor. I'm going to factor out a y so that the inside of that is an even. Right? The other question is the square root of 32, is that a perfect square root? No. So we also want to make sure we're doing that at the same time. So, and you can separate. We can do it separately. So the square root of 32, can I have one of those be a perfect square root? So what times what gives me 32, but one of them is in those perfect square roots? 8 and 4? Yeah, I think there's, isn't it 2 and 16 also though? 2 and 16 is higher, so I'd rather use 16 and 2. Okay? So I'm splitting that already. And then we had just said that I need to take out a y. Okay? So, so we're going to have square root of 2, square root of 16, and then I'm going to take out a y. Now, when I take out a y, remember with exponents, if I have like y to the 9th divided by y, just 1, what am I left with? So when I divide, I subtract, okay? So I'm splitting this up, and I'll still have y to the 8th now. And how was x? Was x okay? Yeah, so x was okay, so I'm going to leave that one as x to the 4th. Okay, so far all I did was split things up. Do you see that? So my 32 became these two. My y became these two. And my x just stayed the same. Right? Are they still all under a square root? Yes. So I haven't changed anything. I just kind of separated them so it's easier to simplify. Okay? So now I'm going to simplify where I can. Okay? I cannot simplify the square root of 2. Can I simplify the square root of 16? What is the square root of 16? 4. Okay? So that'll go away. I'm going to circle what I have left. So this will stay, this will stay. The square root of y. So y is to the first power. So I can't do anything with the square root of y. So that's going to stay. Now, if it's a multiple of the index, I can divide it, though. So y to the 8th is like saying, it's like saying y squared times y squared times, so it's y to the 4th squared. Do you agree that 4 times 2 is still 8? But if I did the square root of that, this goes away as I'm left with y to the 4th. I know that's kind of complicated to think. The shortcut is you just divide this exponent by the index. That's the shortcut, okay? So if I divide 8 by the index, the index in this case is 2, I'm going to be left with y to the 4th. So this turns to y to the 4th. Okay? And then y, or x to the 4th, same idea. The shortcut is just divide the exponent by the index. So I'm going to do 4 divided by 2, and so I'm left with x squared. Okay, now I'm going to put it together to make it pretty. What things are not in an exponent? Okay, so good. The things that are not in the exponent are 4, y to the 4th, and x to the 2nd. Now, it had x first, so if you want to put x first, you can, it doesn't matter. So we could say x squared, y to the 4th. So all those are outside the radical. What is left inside the radical? 2 and what? 2 and y. And I can bring them back together because it's like saying 2 times y. So I'm allowed to bring them back together. This is your answer. Simplifying radicals with the alphabet. All right. Let's try 13 or 14. I already did that with the other classes. Okay. So I want to do 13 or 14. It doesn't matter which one. Do you agree that both of those, the index is 3 though now, right? Okay. So because the index is 3, that means the exponents have to be multiples of the index. So in this case, for 13, those exponents have to be multiples of 3. Okay? Not 2. Okay? Well, 21 is good, because 21 divided by 3 goes in evenly at 7. So we're good there. But 10 is 10 a multiple of 3. No. Okay, so we are going to have to mess with that one. In the same idea, we're also going to have to simplify the number. Okay? So whatever you feel comfortable with doing first. I like to do the number first, but that's up to you. So the cubed root of a negative 64. So if you have, do we have the list of perfects? Are they over here? So here's cubed roots. Is 64 perfect? Yes, but then it's negative, so it's just going to be negative 4, right? Where was I?
Oh, I think you're on the second page. Yes.
There we are. Okay. So 64 is a perfect cube. It is negative though. So in this case, I don't have to simplify it yet if I don't want to, but I can. So this is going to turn to a negative 4, right? All right, what about x to the 10th? Okay, x to the 10th, which number would be a multiple of 3 if I went down? You don't want to go up. So if I take away how many? It would be the x to the 9th as a multiple of 3, right? So I just need to take away one of these. So I'm going to have cubed root of x. Okay? What's left is going to be a cubed root of x to the 9th. Remember, when I multiply these, I'm adding the exponent. So I just split it, okay? And then y to the 21st is still good. So cubed root of y to the 21st. Okay, I'm going to divide the exponents by the index. That's the shortcut. Okay, so in this case, the negative 4 is still out. What is x to the 9th divided by 3? So what is 9 divided by 3? 3. Okay, what is 21 divided by 3? 7. So this, I'm sorry, this is outside, this is outside, this is outside. This, I can't do anything, so that stays on the inside. And so that's your final answer. Have you done a 4th root yet? Let's do a 4th root. Maybe 7. Sometimes it's actually easier than you think though, because I think it's a perfect 4th root.
Oh yeah, it is.
So the index is cubed root of 3, right? The 9 was the 10 minus 1. So I split it. And the reason you want to do that is because you need this to be a multiple of the index. Otherwise, it won't go in. The other way you can think about it is x to the 10th. We want 3's out of it. So I have x to the 3rd, x to the 3rd, x to the 3rd. So this is 3, 6, 9, and then I have 1 left over. This equals x to the 10th. Agreed? But anything that's a 3rd root, 1, 2, 3, will go away. That's what it's doing. That's why it works. So there were 3 of them and those were not. The 1 left got stuck inside still. So that's why it works. It's like you're making little clusters of them. Alright, let's do 17. So 17 is a fourth root. So the exponents have to be multiples of 4. Okay? So this gets a little tricky because 23, even if I go down 1, that's not a multiple of 4. Right? So this is a little trickier. So we can separate it. We can say the fourth root of 625. Okay, and we can say the fourth root of c to the 23rd, and the fourth root of d to the 11th. Okay? Now, in order for the exponents to work, they have to be multiples of the index of 4. Okay? So what is the closest multiple of 23? So 4, 8, 12, 16, 20, right? So 20 is the closest. So I can do the fourth root of c to the 20th. And then how many are left to get me back to the 23? 3, right? Does everyone see how we split that? Does it help to see it that way better, maybe? Okay. And then the 11, I can't go up, I have to go down. So 10 doesn't work. 9 doesn't work. I have to go all the way down to 8, right? So fourth root of d to the 8th. How many did I take away from 11? 3. So I'm going to still have d to the 3rd. Okay, now I can simplify. So these ones, this one, and this one, I can simplify. Is the fourth root of 225 one of the perfects? I'm sorry, 600. Yes, what number? 5. So this is perfect. If you did this in the calculator, you'll find out that it's just 5. Okay? Remember the shortcut here is to just do 20 divided by the index. So 20 divided by 4 is what? 5. So we're going to have this 5, and then we're going to have c to the 5th, and now that's 1. Okay? 8 divided by 4. 2. So we have d squared. What's left under the radical? We have c to the 3rd and d to the 3rd. I can't do anything with those. I can put them back together though. So I'm going to have the fourth root of c to the 3rd, d to the 3rd. That's my final answer.
Wait, the 3rd and the 5th?
They're both in the lead, sorry. Any questions? All right, go ahead and try. So on page 3, go ahead and try number 8 on your own. So go to page 3. Then try number 8. Yeah. All right, so this is the answer to 14, but how did we get there? Okay, so because it's a cubed, right, the index is a 3, then I need to split those so that we get 3s. So we know this is the answer. Okay. I'm going to kind of use the whole paper. All right, so if we take, we're going to ignore the 2 for now. Don't forget about it. We're going to say it in, okay? We're going to do the cubed root of 192. Okay? And we're going to split that into perfect ones. Okay? So cubed root. So what times what is 192, but one of them is a perfect. Good. So 64 is one of my perfects. Okay? So 64 times 3. Okay? But the 64 is perfect, so it's going to change to what? 4, right? So this will be 4. We're going to save that one. Okay? This one can't go any further, but we will save it. Okay? Okay, then we've got to do the inside with that. So we have p to the 7th. We have a cubed root of p to the 7th. We need the exponent to be a multiple of the index. 7 is not a multiple, so we need to take one of them out. Okay. Then the shortcut is divide it. So 6 divided by 3 is 2. So we're going to get p squared. And then we still have this left over. And then the last one is q. The cubed root of q to the 18. 18 is a multiple of 3, so we're good. So it's 6. So we're going to end up with that 4, that p squared, and q to the 6th. And then we still have the 2 on the outside, and we still have the cubed root of p and the cubed root of 3 left over. That's why I circled them. Okay? So the 2 on the outside can just be multiplied by this 4. So that's where we get the 8p squared q to the 6th. And then what's left inside? We have a 3 here and a p here. And that's how we have our final answer. It's easier if you break them up. Okay. All right, I'm on page 4. Before I start an actual problem, when we are adding or subtracting radicals, right? So addition or subtraction, in order to combine radicals, they have to be the same. Okay, so when we're adding and subtracting, the radicals have to match. In order to combine, okay? So for example, up here I did 2 square root of 5 minus 3 square root of 5. Okay? When it's adding or subtracting, kind of think about fractions. If I don't have a common denominator, I cannot add or subtract fractions. But I can multiply and divide them, right? So it's the same idea here. If I'm adding or subtracting, and in this case I'm subtracting, these have to match. The radicals have to match, okay? Then I can do it, almost think of it like an x, like it's 2x minus 3x, right? Kind of the same idea. So then I can do 2 minus 3, so I can see the -1, and then the square root of 5 is 30 with it, okay? So adding and subtracting has to have a common radical. Okay, so right here. Common radical. If it doesn't, you can try and simplify to see if they will, if you can't get a common radical. And then, okay? So for example, number 1, they do not have a common radical, but I can see that I can get a common radical out of them. In fact, I can get the square root of 3 out of both of these. Now what's left over? I'll have 9 and 4, right? And then don't forget the numbers in front. Okay? So what is the square root of 9? 3 times the 3 that was already here. So I'm going to have a 9 square root of 3. Okay? Over here, what is the square root of 4? 2. 2 times 2 is 4, though. That's being subtracted. So minus 4 root 3. Now they have the same radical. Okay? And so what is 9 minus 4? 5. So the final answer is 5 radical of 3. Yes.
So if the second one, the outside is -2, when we do the 2
That's why there was a minus 4, because we're subtracting.
what part of the array subtracting, so it'd be minus negative.
Either way, it's -2 times a +2 is still just a -4. Yeah. Okay, so the biggest thing is just to find the common radical, and then you can add or subtract. The ones that have 3, if you remember PEMDAS or order of operation, it doesn't, adding and subtracting, it doesn't matter which way you do it, you do left to right. Okay, so you would find common radicals out of these, and then you would subtract first and then add in this case. Okay, so you can almost treat it as 2 problems. First, though, you got to find common radicals for all 3. Okay, does that make sense? Okay. And in this case, they're cube roots, so be careful, right? Cube roots. I'm going to let you guys practice this in a minute, but I am going to show you. So adding and subtracting are harder, in my opinion, than multiplying, because multiplying, they don't have to have a common. Okay? And multiplying, we actually did in geometry also, so it's not too bad. Okay, so I'm on, I think it's page 5. Okay, number 11. I'm multiplying. So what I'm going to do is I'm going to multiply the outside with the outside and the inside with the inside. Okay, so when you're multiplying, you do the outside with the outside and the inside with the inside. Okay, and then if you can simplify, you still simplify. Okay, so the outside in this case is 1 times 5. So it's just 5. Okay. On the inside, I have 6 times 8, which is, and then I have x to the 4th times x to the 5th. What do I do when I multiply? Good, I add the exponent. So I'm really going to have x to the 9th. Then you have to go through and simplify, okay? So is the square root of 48 perfect? No. So you can split these. So we have square root of 48, square root of x to the 9th. Okay, so the square root of 48 which one is perfect that goes into 48? 16 times what? Okay. And so 16 will turn to 4. We'll still have this. Okay. And then, what's true about the exponent and the index? They have to be multiples of each other. The index in this case is 2. Can 2 go into 9 perfectly? No. So, we're going to split it and do 8 and 1 left over, right? And then now we just divide. So 8 divided by the index, which is 2, I'll be left with x to the 4th here. Okay, so now I have this and this. So now I put the circles together. If it's on the outside, you can multiply it together. If it's on the inside, you can multiply it together. Okay? My outside are all these ones, 3 ones. Those are on the outside. So 5 times 4 is 20. X to the 4th. Okay. And then what's on the inside? Just 3x? Where did I get 2 from? The index. The index is 2 because it's square root. Because these are square roots.
Oh.
Yeah. So square root of 3x is left over. Yeah, so you always divide by the index. When there is no index, it's assumed to be 2. Right? The last couple that are a little weird are binomials. Same idea, but this gets distributed, right? Because on the outside. So that means that square root of 10 is going to be multiplied by both. Okay? So this one we would end up with 5 square root of 50 minus 2 square root of 20. And then from there, because it's subtraction, you would have to try and get a common x radical and do that, okay? The same idea there. So I'm not going to go through all of that because I'll just get time. All right, so what do these have in common? They're square roots, so you want to try and get rid of them. 10, but then you're going to be left with 5 and 2, and neither of those are perfect either. If I do 20, what if I do 25? No, 25 and 2. Either way, it's going to be kind of ugly. I was like, either way, it's not very pretty. 25 and 2. 25 is perfect, but then if I do 2 on the other side, 10 is not perfect. So. Yeah, that's the only way I can do it. So one of them is not going to be perfect. That's okay. Alright, so let's try those. So here I can do 25 and 2. And here I can do this is 25. So I'm still going to want 2. Right? Because if I do 4 and 5, that's not going to work, right? Okay. That stinks. No, yeah, it's going to be ugly either way. So you can't combine them. There's not going to be a way to combine them. When there's no way to combine them, you just simplify and do the best you can. So I actually do want to simplify this the right way then, as if I was just simplifying. This is a good example then. So there's no way to make those the same. And so when that happens, you still want to simplify. What it means is, though, that subtraction is going to be in your answer, okay? So in this case, we have the 5 times the 5. So we'll get 25 root 2 minus, and then here we are going to go as far as we can. So we'll do square root of 4 and square root of 5. This will give us 2. 2 times 2 is 4. So we're going to have 4 root 5. So this is going to stay as a subtraction for your answer. So if there's no way to get the same radical without getting rid of one of them, just simplify as much as you can. Okay? So that was a good example. All right, last one that I'm going to do. Okay. So let's do 18. So when it has this, it means there's 2 of them. Okay, that's what that squared means, right? And then it's kind of set up like these other ones now. And what you have to do here is FOIL. So you have to do 4 times 4. Right? So I'm going to get 16. I'm going to do 4 times a negative square root of 5. So I'm going to get a negative 4 root 5. Okay? And then I'm going to do negative root 5 times 4. Is another negative 4 root 5. And then negative times a negative is going to be a positive. So plus, and then 5 times 5 is 25. Okay? And then I'm going to simplify where I can. So this gives me 5. So I'm going to get 16 plus 5. And what do we notice about those guys? Are the radicals the same? Yes. Huh? They're both negative, and then adding them, well, and subtracting them, kind of. So remember, kind of treat this like an x. So it's almost like a negative 4x minus another 4x. So it's going to be a negative 8 square root of 5. Okay? So we multiplied, but then when we were combining, right, it became a like term kind of. So that's it. Yep. Because then those can't be combined. All right, make sure you do your homework. Okay, there's page 3 and page 6. I put certain problems on Google Classroom.